This conference will now be recorded.
Very good evening, students. As I mentioned in the last class, we had learnt about the derivation of capillary rise or capillary fall, capillarity, etc. We had already learned. So I thought it will be very good if we solve few numerical problems related to capillary rise, so that our understanding will be again strengthened. So just for that, we are today in this particular session we'll be discussing few numerical problem on capillary rise part, and then thereafter in the future classes we'll take such kind of important topics which are really important and also conceptually rich topic. We'll take one topic from both 11 and 12 syllabus, and we'll first learn the topic conceptually from various good references. After understanding all the concept in and out, we'll solve numerical problem like this. So let us start our discussion for today. So the first question is this one, what says a capillary tube whose inside radius is, that means inner radius, is 0.5 millimeter is dipped in water having surface tension 7.0 × 10⁻⁻2 Newton per meter. To what height is the water raised above normal water level? Angle of contact of water with glass is given at 0 degree. Density of the water is also given, and G we have to take 9.8 meter per second square. So as I said, there are no options given over here. We'll try to solve this. So this is purely from the formula itself we can solve. If you know, see what will be the answer for this. If you know the formula, see what are the informations given over here. The inner radius of the capillary tube, that is 0.5 millimeters. Then surface tension T, let us say, that is 7.0 into 10⁻⁻2 Newton per meter. Then angle of contact theta is given, theta is 0 degree. Density rho is given as 10⁻³ kg per meter cube. G, you know, it has to be taken 9.8 meter per second square. So the question is asking you to find out the height which is raised above the normal water level inside the capillary tube. That means capillary rise. And see here, no mention of consideration of the water inside the meniscus. That means the normal formula will take. Okay, so that is H is equal to 2 into 10 surface tension T, cos of theta, theta is the angle of contact, here it is 0 degree, divided by rho, R and G. Okay, let us put the values of all these parameters. So two T is surface tension, that is 7.0 into 10 to the power minus 2, and cos of 0 degree, that means 1, divided by rho, that is 10 to the power 3 kg per meter cube, r, this is millimeter here, so it is actually 10 to the power 5 into 10 to the power minus 4 millimeter, right? Millimeter is 0.5 into 10 to the power minus 3, and 0.5 also I'm just including over here, so minus 10 to the power 10 to the power minus 4. Rho r and G 9.8. Okay, so look what I get. So here 10 to the power 3, 10 to the power minus 3 from here. Okay, here there will be 10 to the power minus 1. 9.8 you have 10 to the power minus 1 if we write into. Okay, look then what is the thing we are getting. 2 into 7, 10 to the power minus 2. Look in the denominator we get, we can write like this, 98 into 5 into 10 to the power minus 2. So that did 10 to the power minus 2, this, so this is in meter so far. Okay, so this 2 will give you this. Okay, 14 7s are 98, so you get 1 over 35 meter. Now if you write in terms of centimeter, then you know this will be 100 divided by 35 centimeter. Okay, so if you divide this 100 with this 35, so what we get, 70, then you get, see, I think we can go with 8, then 20, so 200 here, so we can go with 5 here, again 25, so we can go for, yes, so we can go for 7. Okay, so thereafter we can actually take approximation of up to second decimal, so this will give you actually, so height is actually becoming 2.86 centimeter inside the capillary tube. Okay, so this is the height raised, height of the liquid raised inside the capillary tube compared to the normal water level outside. Okay, outside the capillary. Now, so the answer is 2.86. So here actually we had used just simple formula to T cos theta by rho RC. That's all. See, why don't we use this one minus R by 3? And when we should use this R by 3? If at all it is mentioned that consider the water in the meniscus. Water in the meniscus. So water contained in the meniscus. If it is mentioned in that way, that please, while calculating the height of the capillary, height of the liquid inside the capillary, consider the liquid contained in the meniscus. In that case, we would have written this formula minus R by 3. Okay. If there is no mention of this particular word, that consider the water contained or liquid contained in the meniscus, then we can go with simply this formula. Okay, so let us solve this problem now. This is again a very interesting problem. Look, the question says a glass tube of radius 0.4 mm. So this is also having inner radius 0.4 mm. If required, I can make this 4 into 10 to the power minus 4. 4 into 10 to the power minus 4 meter. Okay. Find up to what height the water will rise in the capillary. That means capillary rise formula. And here also you don't have to consider the liquid inside the meniscus, content in the meniscus. Okay. So you have to find out what is the height. Okay. You have to find what is the height. If the tube is inclined, okay, if the tube is inclined at an angle 60 degree with the vertical, see, first this was the tube like this, now it is tilted at an angle 60 degree with the vertical. How much length of the capillary tube is occupied by water now? Surface tension is given, and then density of water is also given. Say angle of contact is not mentioned here. So if some cases angle of contact is not mentioned, in that case we should simply take angle of contact is equal to 0, because glass tube and water has always angle of contact very less, that is less than 10 degree, sometime it is 8 degree. And in the previous question we had seen that angle of contact was given as 0 degree. So for water and glass, contact angle we can take nearly 0 if nothing is mentioned. So theta will take, angle of contact will take 0 degree. Then see tension, surface tension is given as the same, because this is water only, so Newton per meter. Water has got density rho 10 to the power 3 meter kg per meter cube. Okay, like this. This 60 degree is not angle of contact. Okay, first we have to find out the height. So let us find out height. 2t cos of theta. Theta is the angle of contact. Then rho, r, and g. Okay, that means 2 into t. T is the surface tension. Cos 0 is 1 divided by 10 to the power 3. This is 4 into 10 to the power minus 4 into 9.8. So we'll get here, see, this and this one can be cancelled out, just very similar to the previous calculation. So this will be 14. So look what I get, 1 over 56. Okay, I'm sorry, so this will be actually 7, so it will be 28, sorry, so this will be 28. 1 over 28, this is in meter, this is in meter. So we have to finally find out what is the length of water inside the capillary tube when it is tilted. Okay, so look here, if suppose this length how much length of the capillary is occupied by water. So this length, let us say this length is L. That is the thing we have to find out. So this is actually H. So this height is going to be same always, even if you tilt it. So even if you, here the concept is that even if you tilt it, the excess pressure, atmospheric pressure, other things are all remaining the same. So with tilting, this height, capillary rise will not be different. What is getting different? See, now earlier this much was filled with water. Now if you tilt it, maybe it liquid may go up to here. Okay, go up to here, but it will be in such a way that the height, vertical height, that remains the same. So now at this point, what we can write according to the figure, we can write, see, this I can think of a right angle triangle. This is the right angle. So this is hypotenuse, this is actually base, and this is perpendicular. So in that way, if we see cos of 60 degree is equal to base, that means height by L, hypotenuse. So we have to find out what is L. L is H by cos of 60 degree. Cos of 60 degree. That means, see, height is this one, 1 over 28. Okay, cos 60 degree, that means half, right? Cos 60 degree means half. So that will go in the numerator. So this is 2 by 28. So this is 1 over 14. This is in meter. But if we want to write in centimeter, then 100 by this. So 100 by 10. Let us do the proper calculation. 100 by 14. So 100 by 14. So this will give you 6. So it is going to be up to second decimal 7.24. Okay, it is going to be 7.24. I see. What is that? Okay, I don't, I'm sorry. Here it will be on, okay, 1. This is 1. Okay, 1/4. So it is 7.14 in centimeter. So this much will be the value of length L. Okay, and if you want to find out what is H, this is 1 over 28 meter. So 100 by 28 in centimeter. So this will be actually nearly 3.57 centimeter. So these are the parameters we had to find out in the given problem, right? So even if you will see here the concept, key concept, what is the key concept over here? Key concept. Capillary rise, height of the capillary rise, height of capillary rise does not change. even when the capillary is tilted or inclined with vertical or vertical inclined. The length of the tube is going to be less above the water in that case, so that's why the length of the liquid inside the capillary will be more. So this is what it is actually, okay? But this vertical height is going to be the same, because see, vertical height depends on surface tension, radius of this tube, contact, angle of contact, density of water. These are not at all changing, right? Even if you tilt the capillary tube. So this is why H is not going to change. Only what is changing is, see, this H is not changing. So this is also H. So what is changing is the length of liquid in the capillary tube. I mean, the length of capillary tube up to which the water will occupy will be changing. All right, I hope you have understood this. Let me go to the next problem. So this problem is again very interesting. Let us first read that and try to solve it. This question says mercury has an angle of contact 120 degree with glass. So angle of contact mercury and glass is given as 120 degree. A narrow tube of radius 1.0 millimeter made of glass is dipped in a trough containing mercury. By what amount does the mercury dip down in the tube relative to the liquid surface outside? See, in case of mercury, how it happens, like what happens inside the capillary. Suppose this is the mercury level outside, this is the mercury outside, and for a capillary tube the level will be little depressed, okay, like this. See, this is dipped down, okay, this is the original level here, but it is dipped down by some h height, let us say. So that height we have to find out by what amount mercury dipped down in the tube relative to the liquid surface outside, okay. So this is also given by the formula H is equal to 2t cos of theta by rho r and g, okay, with the same formula. So let us find out that, so T is given, right, surface tension, surface tension of the mercury is given as this. So that is 0.5 Newton per meter. This is cos of 120 degree, okay, divided by rho rg. Rho is 10 to the power 3, 13.6 into 10 to the power 3 kg per meter cube. R is given as 1 millimeter, that means 10 to the power minus 3. G we have to take 9.8. Okay. So what is cos of 120 degree? You can do this. Cos of 80 degree, 180 degree minus 60 degree, all sine 10 cos. So from here to second quadrant it will be minus. Okay, so minus cos 60. Cos 60 is half, right? Minus half. So these two will cancel with this, but there will be minus sign over here, right? So this is 10 to the power 3, this 10 to the power minus 3. This point and this point we can neglect. So ultimately 5 in the numerator divided by 13.6 into 98. So for the sake of calculation, I'll just take the unit in centimeter. 100 I multiply, and for the sake of calculation, if we approximately take this as 100, these two will actually cancel each other. So 50 by this. Okay, better to just not do that much crude approximation. Let me calculate it. So now 500 divided by 13.6 into 98. 13.6. Okay, so yeah, so this is actually going to be 0.375. This is in centimeter actually. Okay, so if we want to make it millimeter, this is centimilli, so I can write 3.75 millimeter. Okay, just let me cross check whether this value what we have got is correct. Yes, this is correct actually. Okay, this is correct. Okay, minus 3.75. Why minus? Because I am taking this as reference and this is the height. It gets depressed. So minus 3.75. So this minus sign is actually telling you the depression. Okay, depression. H I have just taken the formula same as the rise, but here we are getting negative sign. That means it is getting depressed instead of rising. Okay, so we have got the amount by which the liquid level is going to be depressed is 3.7 millimeter. Okay, so this was the question here. Now let us go to the next problem. I hope you are enjoying this session, because here we are just discussing those questions which are related to capillary rise, and we had already cleared our conceptual understanding about capillary rise, contact angle, etc. So now let us read this problem and try to solve it. So actually this is a combination of some 1, 2, 3 questions. Okay, let us first read. Excuse me. So if a 5 centimeter long capillary tube, 5 centimeter long, that means L, let us say this is 5 centimeter long capillary tube with 0.1 millimeter internal diameter. Internal diameter 2R is 0.1 millimeter. So I can write 10 to the power minus 4 meters, or R is 0.5 into 10 to the power minus 4 meters. Okay, this is what we can write. Okay, open at both ends is slightly dipped into water having surface tension 75 dyne per centimeter square. Okay, so all the parameters are given in centimeter. Why don't we stick to centimeter? Let me multiply 100 here. So we'll get 50 into 10 to the power minus 4 centimeter. Okay, here look, if I multiply 100, so I can write this. The question is asking you to find out state whether water will rise half in the capillary tube. Water will rise halfway in the capillary. First question is that. Then second question, water will rise up to the upper end of capillary. So whether it will go up to half, rise up to half, or rise up to upper end of the capillary. And third option is water will overflow out of the upper end of the capillary. Explain your answer. That means, there are three options: whether the liquid will rise inside the capillary halfway, or it will rise up to upper end, or you have to explain if whether if it is getting overflowed. Okay, so first of all, let us find out what is H. Here contact angle is not mentioned, so we'll take that as 0 by default. Water and glass, right? So 2 T is 75 dyne per centimeter. Cos theta is 1 by rho rg. Rho, it is, I don't know whether it is, yes, it is water, right? Diameter is slightly deep water, yes. So your water in CGS unit, rho will be 1. R is given as 50 to the 10 to the power minus 4. G, we have to take 980, and contact angle 0. Okay, 981 it is taken. Excuse me, yeah. So what we are getting here, cos of 0 degree is 1. So look, then we get 2 into 7, sorry, 75. This is minus. So this will be 10 to the power 4 here in the numerator. This is 50 into 981. Okay, if you do the calculation properly, then what you are going to get this in centimeter. Let us do the calculation. So this is 150, right? So 25, 3, 25, 2, this 2, this 2 cancel each other. Then 981 divided by 3. So this is 10 to the power 4. divided by 327. Now you have to divide this one. Okay, so this will give you some 30.58 centimeter. So this is just matter of calculation. Okay, so we have got the capillary rise. Okay, if with the parameters given over here, the rise of liquid inside the capillary tube should be 30.58 centimeters. But this capillary tube is 5 centimeter long, just 5 centimeter long, right? So here we can see the height, it actually rising is much greater than 5 by 2, isn't it? So first possibility is not possible. This is not possible. Then second one, water rise up to the upper end. This is true since the capillary tube is insufficient. What will happen when a capillary tube is insufficient? See here, the length of the capillary tube is 5 centimeter, but height capillary rise is seen around 31 centimeter, right? And L, the length is just 5 centimeter. So in this case, actually, we have learned in the previous day that in case the capillary is insufficient, then what happens? In that case, liquid go up to the upper end and then it spreads out. Okay, it spreads out such that h, the height, into r, the radius of the meniscus. Sorry, this is capital R, and this has got smaller radii. So this capital R is the radius of the meniscus. So it will just go up to the upper end, okay, and then spreads out because this is constant. This we have learned in the theory part. Okay, this particular multiplication h into r will be constant. So if h is less, then r will be more. So it will spread out. It will first rise up to the upper end and then it will spread out to just have a balance of this value. Okay, or hr is equal to constant this value. Okay, and third point was whether the water will overflow. The answer is no. We have seen in case of insufficient tube length, the liquid will not overflow, rather it will go up to the upper end, and the liquid meniscus will adjust the radius of curvature in such a way that hr, multiplication of h r, so it will be h prime, then r prime h prime is equal to hr. That means in normal case, if the capillary length is more, then h into r is constant, and if the capillary is also having less height, in that case also the radius will be adjusted in such a way that h prime into height, h prime into the multiplication of the radius. Okay, this value remains constant. Okay, remains constant. All right. So these things are explained then one by one. See, so it will not rise up to half because it is much more than half. H is 30 centimeter or nearly 31. Here the length is actually 5. So it is 5 by 2, much larger than 5 by 2. Second is water will rise up to upper end. of the capillary. This is true because we have seen that the capillary tube is insufficient in length to accommodate the rise in water inside the capillary. In that case, the liquid will rise up to the upper end and spread it out to adjust the radius of the meniscus in such a way that H into R, this remains constant. Okay, all right. So let us go to the next problem. Maybe this is the last problem for this session. I hope yes. Okay, no, we have two more problems which we are going to solve. Okay, so these are similar problem almost. So the height of mercury barometer is given is H. When the atmospheric pressure is 10 to the power 5 Pascal, the pressure at X is how much? This is very interesting problem. Look, this here, this is the point where X is denoted, and you have to find out actually the pressure. Okay, pressure over here. See, this height is total height is H, and this much height just up to X is H by 5. Okay, and look, this point and this point outside, they are at the same height, or they are at the same horizontal level. So here if I say atmospheric pressure, then this also will be atmospheric pressure. Okay, atmospheric pressure. So look, then the pressure we have here at this particular position is the total H rho and G. This is equal to atmospheric pressure. Okay, this is actually atmospheric pressure here up to this point, H rho G. Now what is this one up to here? What is the pressure? The total pressure is atmospheric pressure, and if we find out, let us say this point, this point is P, this is Q, and this Q prime. So Q prime atmospheric pressure. Okay, so at the Q prime, what will be the pressure? Or at the, okay, Q prime pressure is this one, so that is actually atmospheric pressure. So what is the pressure at P? What is the pressure at P? So pressure at, okay, we have to find out pressure at X. So look, then what we say, so pressure at X plus pressure at P. Pressure at P. So these two will be exactly equal to the total height, pressure of the total liquid column, right? Okay, pressure at, I mean P means, no, I do not say, I should not say P. Pressure due to this height, this column height, liquid column is by 5. Okay, so let me just correct it a little bit. So this I can directly write pressure at X plus, so this much pressure plus height of this pressure due to this column height of liquid. So H rho G, H by 5 rho G, okay, is equal to H rho G, that is atmospheric pressure. So Px will be H rho G minus H by 5 rho G. So this is actually 4 by 5 H rho G. So this will be 0.8 H rho G. So H rho G now we have to find out. Okay, atmospheric pressure was given actually. Okay, H rho G is 10 to the power 5, right? So 10 to the power 5 is given already. So this is 0.8 into 10 to the power 5. So this is in Pascal. So option B will be the correct answer for this question. Okay, so we have got another problem which we are going to solve and then we'll stop. So this question, I hope you will be able to find out the answer now, because the previous question was similar to this. A liquid of density rho and surface tension sigma. Surface tension sigma is given. Rises in capillary tube in inner radius capital R. Inner radius of the capillary tube is capital R. The angle of contact between the liquid and glass is theta given. The point A lies just below the meniscus, in the tube, and the point B lies at the outside level. Okay, lies at the outside level of liquid in the beaker as shown in the figure. So this is actually this much. Okay, so this much is actually H rho and G. This is actually pressure at B. Okay, pressure at B. And as you know, pressure here. Okay, so the question is the pressure at A. Pressure at A. How much will be the pressure at A? Generally, this capillary height we write what we write. See, atmospheric pressure is PA is H rho G, that is atmospheric pressure. Or PB. Pressure at PB is atmospheric pressure. Okay. Now, what is this height in terms of this? We know 2s, 2 sigma cos of angle theta by rho R and G. This is fine. So we have to find out pressure at A, right? Actually, if we consider this point, here we have certain excess pressure, that is this one. Okay, at the concave surface. Okay, this excess pressure is, that means 2s cos theta, 2 sigma cos theta by R. Okay, this much is the excess pressure, that means PB minus this. Okay, this will be the excess pressure at this particular point actually. Okay, here. So PB is the atmospheric pressure and here it is actually excess pressure. Just below, it is said A lies just below the meniscus. That means we have to take this point this point here, just below the meniscus, where the excess pressure is there. Okay, and how much is the excess pressure? That is 2 sigma cos theta by r. That is the, so this is actually the answer to sigma cos theta by r. So option B will be the correct answer for this question. Okay, I think PB minus H rho G, P atmospheric pressure minus this. So this is also true, and this is H rho G, PB minus H rho G. This is also true. PB minus H rho G. Let me just cross check once. So the question says a liquid of density rho and surface tension sigma rises in a capillary tube of inner radius capital R. So PB is atmospheric pressure. Fine. So PB minus 2 sigma cos theta by R. This is fine. This answer is fine. These two are at least fine. I'm saying PB minus H rho G. Let me take this. Actually, H rho G is the PB. That is atmospheric pressure. So this I don't think. This I don't think. And it will be directly H rho G PB minus. Okay, guys. So I'm just getting a slight doubt. These two are fine according to me. Let us clarify it later in the next class. Okay. So with this, I'd like to stop it here for today. Next class, as I mentioned, we'll take topic wise. Okay. So that way, it will help us to grasp the knowledge, and that will help us to understand how to solve the problems, numerical problems also. Okay, so this thing will clarify in the next class. So thank you for your patience. Bye for today.